separate talks, half-hour talks in here, and I want to consider two different kinds of stars. And the common part of this whole thing is that what you learn by pushing away from the optical spectral region in order to get insights onto what's going on in stars, both metal poor and metal rich. And that's why I have the Hubble Space Telescope there and its STIS spectrograph. In the middle there's Spectral Observatory 2.7 meter and a new, relatively new infrared spectrum, high-resolution spectrograph, Igrens, the fourth picture, and Gemini South, and that's where Igrens is right now. Okay, so if I had to sort of give you one slide, this is the one slide I give in most talks. It sort of summarizes why I am fascinated by chemical compositions of stars. And how did somehow the galaxy began with nothing but hydrogen and helium and a drop of lithium. And now we have this wondrous array of elements. And a lot of those elements actually will be touched on in this talk. Here's a formal outline. In the two halves are in red up at the top there. I want to talk about the iron group elements in very metal poor stars. And those of you who work on stars might have said, wait a minute, wasn't that done a long time ago? And I'll convince you that there's new stuff to learn. And the second part, I'll be talking about light elements in basically mostly metal-rich stars, with one exception. And I remind everyone of the standard abundance definitions, the bracket notation, bracket X to Y, that's pretty much known. What is a little less standard is the designation of log epsilon, which is essentially an absolute abundance on a hydrogen equals 12 scale. And, oh dear, is there a way to sort of check the spacing here? All right, we're going to have to live with this, folks. I want to make sure that, first off, the definition of metallicity is clear. Metallicity is going to be equated to the iron to hydrogen bracket ratio, for want of a better definition. And the fact that I don't mention many names doesn't mean they shouldn't be given credit. They would fill a whole slide by themselves. So I'm speaking on their behalf. Okay, first part. Iron group elements, which is I formally define as scandium through zinc. And that will be the entire set of elements that I talk about for a while. Low metallicity, iron group, well, we know what made them. It has to be very short-lived, massive predecessors that spewed out a bunch of iron group elements into the interstellar medium where they were picked up by the stars, low-mass stars, that are still around today, and we can observe them. You've seen in almost every elementary to advanced textbook on stars this kind of diagram that shows sort of the onion skin. As you go deeper and deeper in the burning, you get heavier and heavier elements. Okay, so we know that this had to happen because the stars that I look at are 13-ish giga-years old, and so only really the massive stars can precede them. Look, one nice thing is that theoreticians, stellar interior nucleosynthesis theoreticians, can actually predict the elemental abundances for the iron group that come out of these stars. And that's really a nice thing, because then you can ask how, you can actually challenge the theory. Challenge means sort of test the theory rigorously. And you can go from solar metallicity stars all the way down to -3 in the predictions. Chaki Kobayashi published this paper in 2006, and she had a general review of how the predictions here match or don't match the observed abundances as of 2006. Okay? Here's the state of the art, sort of, as sort of first enunciated by Andy McWilliam. Now, look, folks, I have my name there in ink, and it's not because of my ego. It's because I want to make sure that you know I was part of this paper, because I'm going to show that most of it I think is wrong many, many years later. Okay, this paper caused quite a stir back then. At very low metallicities, say metallicities -2.5 and below, what Andy showed was that the chromium to iron makes a significant drop. That is, the relative abundance of chromium is much less compared to iron than it is in the solar system. He also suggested that manganese was extremely underabundant. Cobalt did the opposite. It jumped a considerable amount, such that the chromium to cobalt is like -1 at low metallicity. And then finally, a result that had been known a little bit before that, copper also declines. So there's this huge change at below metallicity of -2 when the iron peak elements in metal poor stars tend to just depart from their solar system compositions. Well, I wish that were true. Later follow-up to the McWilliam work confirmed and refined it. That is, the confirmation was that it narrowed the star-to-star scatter because for instance, like this so-called first stars group by Carell et al. That came out in 2004. Well, they had much better spectra. They had more control of their analytical methods, et cetera, et cetera. So a lot had been improved in the decade between McWilliam's work and the Carell stuff. And the Carell did more stars also, but basically the trends stay the same. The cobalt is overabundant and the chromium is underabundant. And so essentially what McWilliam et al. Predicted turned out to be true. Other surveys did it, but something was really wrong. Kobayashi points this out in her 2006 review, or the matching between the observations and the syntheses. Now I'm supposed to know how to operate this. Aha! Okay, in both pictures there are the galactic chemical evolution models from Kobayashi about what should be the chromium abundances, chromium to iron ratios. And you know that what they predict is that it sort of stays like the sun, sort of, maybe rises a bit. So here are the observations. And indeed, the observations are that chromium actually goes down. But that's only if you use neutral chromium transitions. Even the chromium transitions that they knew back in 2006 looked like there was no effect whatsoever. So if you only looked at chromium 2, you'd say, well, predictions and observations match fine. McWilliam is wrong. Okay, but look, there's only one number of chromium atoms in the atmosphere of a star. There can't be this difference between chromium 1 and chromium 2. It makes no common sense whatsoever. So how are we going to actually make any progress? The first thing that everybody has to understand is that in the typical stars that are in the halo, that is either red giants, those are low gravity, cooler, and high gravity main sequence stars. Everything is ionized. All the ordinary elements, there are a few exceptions, but almost every element is completely ionized. This plot from a paper we did a few years ago on one particular star shows the ratio in logarithmic space here of the number density of ions compared to the number density of neutrals for these iron group elements. Now, it's a simple Saha calculation that you can do on your laptop in half an hour, okay? But what it says is, and this is a factor of 100, the ratio of chromium of all the elements compared, ions compared to neutrals. They're all ionized, okay? So you better get your abundances from the ionized lines, because that's where the element is telling you the truth, okay? Where are the ionized lines? Anybody who has taken some detailed look at atomic physics knows this kind of trend, that the stronger lines, and I'm using cobalt here, the stronger lines, and I combine cobalt 1 and cobalt 2, they're all in the ultraviolet. And that doesn't matter if you're dealing with metal-rich stars, because I can find a lot of cobalt lines in any part of the optical spectrum. But by the time you get to low metallicity, the lines you're barely observing here in say the sun go like that. Well, 2 orders of magnitude. Each tick is an order of magnitude. If you have metallicity -2 stars, like the sun, you drop all these lines to absolute invisibility. So we still have problems. A pause that I must give here is to thank the atomic lab physicists at the University of Wisconsin for an incredible job they have done. Because not only have the telescopes improved, not only have the instruments improved, but very, very, very quietly, the atomic physicists have gone back to the lab and gotten much better transition data. I could, at the end I can tell you why it happened, how it happened, what changes happened. But there's Jim Lawler. And I have two ways to show their contributions. I can do it with a diagram that I'm drawing a blank on. Help me. Periodic table, sorry. I can do it with a periodic table in which I color code which of the elements and which of their species, neutral or first ion. The Wisconsin group has published excellent transition data. But you'll notice that that's the entire group of Iron Peak elements now. There's another way you can do it. There's the list of their publications within the last 20 years, and they're all available online. But in other words, every one of the lanthanides, which I'm not talking about today, I talked about them last week in Sao Paulo, and all of the iron group, both neutral and ion, have been studied except copper and zinc, which don't have many transitions anyway that you can get at. So basically, they can tell you, look, we have all the data you need now to do reliable abundance work. Okay, here's what happens when you go from a solar Metallicity star, in particular our sun, and you simply take comparable temperature stars, comparable gravity stars, and you drop the iron metallicity to minus 2.2, 29, 29, 29. So this is 100 angstroms, my friends. There are less than 10 lines that you can positively identify. And it's no wonder that if there's some question assigned to the abundances derived in very metal poor stars. Whoops. The trick is to go down to the ultraviolet. Not only does the diagram of line strengths show that, boy, the line strengths should be much stronger in the ultraviolet, but the actual spectra show that too. So here are HST STIS spectra from in the 2300 to 3050 angstrom range, in which, just for fun, I have a solar light. There's no atlas for the sun down in this range. But here's Alpha Cen, which is certainly a solar type star. And of course, there's no continuum. It's all really the magnesium depression there. So no one in his right mind would want to study that star with ordinary spectroscopy. Look at minus 2.2. It's almost sort of workable. By the time you get to minus 2.9, it looks like an ordinary, easily studied star. And I could argue, if I had time for it, why analytically it's also easier, as long as you stick with stars that are warm near the main sequence. And the 4 stars you're seeing here are, oops, boy, every time I touch this, it's doing this. Yeah. The 4 stars here are all very roughly the same. 6,000 or plus or minus in the temperature. Gravity nearest the sun. Metallicity, all less than minus 2. And they're all basically solar kind of positions in the HR diagram. So be careful now. Okay, first result. The star that was in blue was the star with metallicity minus 2.2. It's a very bright star. It's got really excellent atomic data. It's got really excellent data all the way from the deep red down to 2300 angstroms. The Lawler group has provided tons of absorption lines with good transition probabilities. And with that, what we did, and that includes Lawler, includes John Cowan in Oklahoma, places like that. What we did is we did this massive line measure by syntheses. There were about 1,100 different syntheses here, and we got every iron group element in that star transition. I didn't say that right, sorry. Transition for all the iron group elements, both neutral and ionized, all the way down. And they're a massive number. what should you take from this picture? You should take the fact that both neutrals and ions have been measured in 7 of the 10 iron group elements. And they give, according to this diagram here, the same abundances. Neutrals and ions say that the abundances of particular elements are the same. Therefore, when you have that many elements telling you that you've got the temperature about right, you've got the gravity about right, that it's simple. That you have things nailed down now. Everything starting with titanium and ending up at nickel is giving you the same answer, no matter what kind of lines you look at. Okay? So, where is the cobalt overabundance? Well, not much. Where is the chromium underabundance? Well, not much. There are some fussing I could talk to you about in a few of the transitions. But what is really important here is where I think I have destroyed faith in a cobalt overabundance and chromium underabundance. Look at the first 3, the lightest elements of the iron group. I have more to say about them in a couple of minutes. They're significantly above iron in the differential metallicity. They really are overabundant compared to iron, and it's not in a subtle way. It's a factor of 2, factor of 3. Okay. It's hard to make that kind of mistake when you've got those good data and those good transition problems. Boy, every time I touch this. Let's see, sorry. Okay, so we did the other 3 stars after this first one. Note the quotation marks around the word survey. That's the whole sample. It's likely to be the whole sample for the next N years, where N is very, very hard. It took us 6 or 7 years to get HST to approve the proposal for just these 3 lower metallicity stars. If I apply again, they won't give me the time. It's not because I hope it's probably a good proposal, but the crunch for time on Hubble Space Telescope is so monstrous that they're not going to give more stars. So 4 stars will have to be representing what we know about the HST view of low metallicity stars in the ultraviolet. So there are the 3 stars. Looks kind of similar. And if you combine all of them, of the 3 stars, the black, you just sort of do an average. Not only do they confirm that scandium, titanium, vanadium overabundance, it looks like it's even larger at minus 2.9 than it is 2.3. The error bars argue that it may not be significantly larger, but it's always high. Okay. This work, again, I would point out 2 people, Ian Roederer, who actually submitted the HST proposal. He's a postdoc, a young faculty member at University of Michigan, and John Cowan, who has been a theorist of nucleosynthesis thing at the University of Oklahoma for many decades. Okay, alrighty. So when we get this result, we say, now wait a minute, why isn't anybody talking about this? There have been lots of stars studied for lots of elements that at low metallicity. But it turns out that we think they just missed them. Because if you look at the surveys of metal poor stars in the iron group, look at the scandium to iron ratios from star to star. They all are on a line. No matter which of the surveys you look at, you notice that there's a direct correlation between scandium and iron. Let me try this again. Direct correlation between scandium to iron and titanium to iron. Why haven't people talked about it? I think the answer is going back to what I started with, how these stars look in the optical spectral range. It's such a limited number of transitions that have been used in the past. Nobody's fault. You have to go way down to the ultraviolet, near ultraviolet, to find them. So because most people use optical spectra, blue, red spectra, there aren't many scandium lines. There aren't many iron lines. There aren't many titanium lines. So people just didn't bother trusting them anything more than, about the same as iron. And people have just missed this obvious correlation, which is sort of gathered here in a mess here. But it's very striking. What about vanadium? Same thing. It's very solid, folks. And I should have put this in the last one, but this 45-degree line is meant to represent equality, and it's just shifted so that it passes through the mean of our stars. There's no astrophysics there, folks. It's just guide to the eye. But it's sort of kind of a 45-degree, one-to-one correlation, okay? What if you keep going to heavier elements in the iron group? Nothing shows up. For instance, here is nickel, and nickel to iron versus titanium to iron. I think you will accept the fact that there's no correlation between them. There's just a mass of points. Very, very sharp for scandium. Nothing once you get around, or nothing obvious. Okay, back to the cobalt problem. If I go back, if you take a good look here again at this, you say, wait a minute. If you go to cobalt here, here's your overabundance from neutral cobalt transitions. Here's the underabundance from ionized cobalt, or slightly underabundant. I think that this is a screaming signature of some atmospheric LTE something issue going on. I believe firmly that what we have found is that cobalt overabundance effect was, by the way, the theoreticians, nucleosynthesis theoreticians could never produce anything like a cobalt overabundance in their calculation. And keep nickel at its bland position, nickel to iron's about 0. And why suddenly is cobalt to iron very high? They could never do that, and I'm suggesting that because it isn't real. There it is. So here's the massive data, almost all of which is from cobalt 1. Here is our result for the cobalt, neutral cobalt lines. Here's our result from the ionized cobalt lines. I think there's no effect here. My guess, and I'm not claiming that our ionized cobalt answer is perfect, but I'm saying that there is no evidence for a rise in cobalt at low metallicities if you look at the ionized cobalt lines. Okay, let's talk about interpretation. One more thing on the analysis. I will just mention that I have mentioned non-LTE several times here. It's not what I do for a living, but we now have somebody recruited, Rana Ezzedine, who has been a postdoc with Anna Frabel at MIT, but now she's starting a faculty job at University of Florida. This is what she can do well, and so we're going to hand our data to her and see if she can come up with an interpretation. Again, the challenge, there have been non-LTE papers. If you look in the literature, they deal with one element at a time. And remember, what we've shown is that for most of the iron peak elements, neutrals and ions agree. So it's cheating if you just consider one element and try to explain its anomalies. You've got to do all of them. Because if what you do for one element makes the other one then fail in its ionization balance, that's wrong. Okay. Interpretation. 2 slides. There's a nice paper by Curtis et al. 2019. In that paper, there's a very nice set of tables that tell where their best estimation of what iron group element actually went isotope by isotope. They say where they are probably made in the interior of a massive star before and during blow-up. And so I just used arrow to point to the ones, and it basically, what you'd imagine, that the lighter elements are mainly synthesized in the outer layers. Something like oxygen fusion, that's outer layer, sorry. And then it gets very, very mixed, from classical silicon burning to silicon burning, which they call partial or incomplete, to silicon burning where they have to sort of fudge the parameters in their models in the computer. They have to change the proton to total nucleon ratio and stuff like that. So it is a hard problem, and they've got a very difficult task. So in the Curtis et al. Paper, the final thing is they took that star in blue, HD 84937, and here's their best attempt to fit it. This was when they would use older interior models, Woosley, Hager, Weaver, 2002, and the update by Woosley and Hager changed a lot of nucleosynthesis data, including the neutrino rates. And based on mostly this thing here, I'd say these are my bullet points. It's pretty good agreement now for below Metallicity stars. They do not predict cobalt overabundances. Scandium and zinc have big scatters from model to model. As a matter of fact, all the theoreticians will tell you that they have no way convincingly now to predict the amount of scandium that's coming out. It's just a difficult element to synthesize. There's a lot more work to be done here. Hopefully that when we can get to the point of getting believable NLTE calculations, we'll push down not to the vacuum ultraviolet, but at least there's a lot of data you can get down in below 3,500 angstroms from ground-based telescopes. And that's where to go next for a larger survey. So this is my summary of the first half of the talk. We think it's not that we're more clever than the people in the past, but we were able to expand the wavelength range dramatically and expand the confidence we have in the atomic data parameters. Enough lines and for the right ionized species to do. We think we are firm in saying there is no chromium and underabundance, no cobalt overabundance, which will make the theoreticians happier. But we do believe that scandium, titanium, and vanadium really are correlated. They go up and they go down, but they go together. So nucleosynthesis theorists have had a nice time. Now they've got to get back here and explain why the first three elements of the iron group are correlated so strongly in the early days of the galactic nucleosynthesis. Light elements. Now we're going to shift focus here. The first few slides will be sort of the first project we did using infrared spectra to do transitions that are mainly of the lighter iron group. Those of you who are veteran stellar spectroscopists know that often the light elements are way out in the J, H, and K bands. And I've highlighted them, and I have a loose definition of lighter elements here. So these are the ones we've basically been able to study with a relatively new instrument developed by South Korea and University of Texas. It's called Igrens. And I'm panicking because I should have written what Igrens means. It's put in your infrared, grism something. Go look it up, okay? I've completely forgotten, but it is an acronym. It was done under the leadership of Dan Jaffe. And the nice part of it is it's such a simple, elegant instrument. It covers the complete H and the complete K band. The resolution is 40,000, which is on the high side. And it can move around. And I'll show you why it can move around. So first thing, it's small because its gratings are small. One of the classical problems is getting a shell grating when you go out into the infrared to be able to produce a large wavelength coverage and be compact enough not to require the size of this room. Okay? So they developed silicon immersion gratings. Silicon immersion gratings are ones where the light is allowed to go through the silicon straight, hit the grating on the back, and rebound. What that does is essentially double the diffraction that the shell grating gets, and makes it possible to have a relatively compact grating to deliver extremely high dispersion. Okay, and it works only in the infrared because silicon will block the light in the optical, right? So, but this is for infrared. More details can be talked about offline. Here's an optical layout. One of the things they do, there's one shell grating, but there are two different cameras. One is for the H and one is the K. But other than that, I would say that the other thing you have to sort of understand is it's mainly like all other shell spectrographs. There's nothing more, the cleverness is in this grating. Um, and maybe I'm trying to just sort of say this in a way that makes sort of common sense to everyone, including myself. It's definitely a PI instrument. The Igrens team so far has been the ones who have actually used this instrument. They prefer to do that themselves. But it's like it was a facility instrument. It's now routine to use it. And again, they can move it around the world. The complete H&K, no moving parts. When I was on one of the Igrens observing runs, I was allowed to do the one thing that they do every night in moving something. I could unscrew the cover for the instrument and take it off. That's it. You do not change a thing the entire night because it has the complete coverage. Okay. Here is give you a sense of scale here. Here's why it can be moved around the world. Here's good idea of how big it is. It's this whole thing. This is the 2.7 meter telescope. It's a CAS instrument at 2.7 meter. And if you could do that, then as long as you can get the focal ratio acceptable to other telescopes, just take it in the airplane, move it down. Okay. Give you a quick census. So here is a red horizontal branch star, RHB, which will be called subsequently in the field, red field. It's a relatively bright star. And here's an Igrens H-band spectrum. And I deliberately showed even the parts of it that are totally killed by telluric absorption. And I've shaded them, but that's what you get. There's a rich spectrum here. Now, same spectrum you had before. I've trimmed off the garbage regions. And this time, here's the red horizontal branch star. And here is one of the classic, very, very metal poor stars, HD 122563. The spectrum of this was obtained during the shakedown of the whole instrument. And we observed it just for fun, thinking we wouldn't get anything. But there are lines there. And lines that turned out to be unexpectedly useful. Now here, in the H-band, the big competition, if you would have it, is with Apogee. And here's an Apogee spectrum. Apogee didn't get this star. It's too bright for them. But here's a comparable star, a red giant of low metallicity. And here's the Apogee spectrum of that star, and compared with the Igrens spectrum. Apogee doesn't get, it gets half the spectral resolution that Igrens does. It doesn't have as much spectral coverage. Looks terrible, doesn't it? I mean, but they've done good work with it. But it's nowhere like what we can get with Igrens. Okay? They can do billions of stars. We can't. Let's do the same comparison in the K-band. There's obviously no Apogee spectrum coming up here, because they didn't do the K-band. So here is a red horizontal branch star. Here are the CO bands in particular. They just pop out. And here's HD 122563 with CO still hanging in there. Okay, why would we be interested when we can get some of these elements in the optical? Here is sort of a strength plot in which it's a crude thing. It's basically the Boltzmann equation. With a single species, in this case silicon 1, it is the log GF, which is as its stronger transition, probably it goes that way, and theta, the old-fashioned 5040 over T, at times the excitation energy chi. So that gives you roughly relative strengths of different spectral features, sort of independent of wavelength. And of course, like all things, silicon has most of its strong lines in the ultraviolet, with Igrens were at the opposite end of the spectrum. But look here, when you're working on a metal poor star, here are the two lines of silicon, only two, which are used. And each of those has multiple problems associated with it. Again, that's 5 minutes offline. 3905, rarely 4102, but trust me, you don't want to trust silicon abundances in metal poor stars from optical data. You try to go to the same, well, why can't I just go to the red and the optical? Very, 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 very weak lines. Instead, oh, here in the J and the H and the K band, hey, there are some promising lines. Can we detect them? Of course, the answer is, or I wouldn't say it that way, yes, we can. So here is the bad 3905 line. It's bad in 5 different ways. Here is the 4102, 4103 line. It's on the side of H delta. Here are very, very, very weak lines. Look, it's a few percent deep. In HD 122.563 in the red spectral, yellow-red spectral region, and if you didn't get spectra this high signal to noise, then you'd never see them. Instead, go out to where Igrens has gotten these lines. They're very pleasant to analyze. So for very middle poor stars, great. This, you will get a much more reliable answer if you go to the infrared. Don't believe anything from the optical. Another thing, this is what I always tease people. This is a wonderful question for a stellar spectroscopist master's exam. Why, when OH lines are, the OH is very much a minority species. If you look at the Arcturus, if you look at the sun, the lines are really weak. So now you drop the metallicity by minus 2.7, and they're still there. The question is why. We can talk about that later. It turns out to be 3 regions going exactly in the same direction. On from the test very metal poor star. Red horizontal branch stars are defined here. They are definitely they're evolved stars. They are most likely helium core burners, and they are very much to the blue of what is the standard red giant club for metal-rich stars. My friend, who you'll see in the next slide, Milike Afshar, and I have been conducting a big survey of red horizontal branch stars, trying to figure out what they are. But we decided to use Igrens for a few of them. And actually, we've gotten about 60 of them, but we published a paper on the first 3. And they're the H-band and the K-band spectrum. It's a rich set of absorption lines. And here are some highlights. I don't want to bore you with the details of this work. First off, in the infrared, you can find elements that you can't get in the optical. Here are 2 examples, or can only get poorly in the optical: potassium and phosphorus. You have to do spectrum syntheses. You can't just do equivalent widths, because, for instance, the potassium lines have blending other species in their wings. Be very, very careful. So you have to do the grunge labor. On the other hand, trying to get the carbon isotope ratios, which is basically done in red giant spectra in the optical with one triplet of lines at 8,003 angstroms. That is, yeah, here it is. And look in R3, can you even claim that you're seeing carbon 13 N lines there? I don't believe it. Right? I don't think we even put a value in our first paper, optical paper, for this star. Now go out to the CO bands, and this 13 CO is wonderful to analyze. We can get a very accurate carbon isotope ratio. Other things we've discovered. You can do, out in the infrared, what people claimed you couldn't do. You can do a standard stellar spectroscopist method to get the temperature. That is, you flatten the trend with ion excitation energy. And here is for Arcturus, and here is for one of our stars, 14809. It's a wonderful thing. You can get the temperatures from infrared data, which has always been a problem. Final thing is just for fun. Be really careful. Okay. In this case, we were having trouble analyzing titanium. The lines looked too fat. Until we realized there are 5 isotopes of titanium, and those minor isotopes act to significantly broaden the lines. You couldn't see this in the optical. It's too small. Once you get farther and farther out into the red and the infrared, it starts spanning out, and the isotopic effect. And so we were able to actually detect that in lines of our star. Of course, this is not a stellar spectrum. This is a lab spectrum. But you can see the effects in the stellar spectrum. So, you make a summary. The 3 stars, we had already done the optical analysis and published that. And now here is our result from the Igrens H and K. And first off, you can just see, just scanning element to element to element, they almost always agree. And that was not a given, because the transition data are very, very weaker from the lab in the infrared than they are from the optical. So that is good news. So the point is that you can do steady spectroscopy just from the infrared. Okay? But we weren't interested as much in field stars as we are in open cluster stars. So we have started a program to look at open clusters, and our ultimate goal, which I'll get to right away, is that what we want to do is be able to use Igrens to do chemical compositions of open clusters toward the galactic bulge. And toward the galactic bulge is where it becomes impossible to get high resolution optical spectra. The reddening is just too big. Well, what we're doing is we're doing sort of the background work now. If those of you who are in stellar astronomy will recognize these names as three of the very standard open clusters. And for each of these, we have optical data. For these two clusters, we already published the optical analysis. And now we're going through with the infrared analysis. Our real goal, again, is to push forward. Beautiful color magnitude diagrams now that Gaia 2 has reported in. And just a summary of the differences between these clusters. Higher reddening here, not much reddening there. Okay, so what do we learn when we actually look at those clusters? First off, there's yet another way to get temperatures. Not only can you do the standard stellar spectroscopist tick of trying to measure equivalent widths of iron 1 lines, comparing low excitation with high excitation iron lines. That's been done for 50 years. Okay, but you can do something with line depth ratios. David Gray pointed this out years ago. And now, if I was on a Mac here, it would be possible to see that. But you look at line pairs. Typically, one of the lines is like vanadium 1 or scandium 1. And another is a higher excitation, say, iron 1. And again, just appealing to Boltzmann, just appealing to Saha, there's a wild change in the low excitation vanadium lines compared with the higher excitation other lines. So much so that they're calorimeters. And you can see this happening, for instance. Look at this pair. And that's only a change of 900 Kelvin. And it's really, really sensitive. So that's been done in the optical a long time ago. But now, Fukui et al. Have identified similar pairs of calorimeter lines that can be used in the H-band. Okay? What happens when you apply this to stellar spectra? Stellar targets. In the optical, we we worked on NGC 6940 and found that there was a good match between the spectroscopic temperatures done the old-fashioned way and the line depth ratio temperatures. So those are the blue points there. And you say, well, that's good. There's one point that doesn't look the same, but we got to look at that more because we don't have enough calibration points. Now you go to the infrared, same answer. So there are two different ways to get temperatures that way. The only problem, that's one of the dirty secrets about doing stellar spectroscopy in the infrared, there is one ionized titanium line that received an Apogee letter for its publication because someone found a useful iron group ionized transition. There just aren't any others. No iron 2, nothing like that. And so it's very, very difficult. That's the bigger problem to get gravities. Okay. Well, look. What we do is we do some syntheses, and these are pleasant. Yeah, there's sulfur, and there's phosphorus, and potassium. And we chose the star MMU 152, which is a member of NGC 6940. And the reason why we chose that star for display here, but these are not unusual results, is because what you see here. And what you see here is that the red synthetic spectrum matches beautifully, and the other two synthetic spectra are just wrong. red synthetic spectrum is for an isotopic ratio of 6, which is not normal for a high metallicity population 1 star. Okay? It's highly unusual. Typically 20, 25, that's what they normally are in red giants. And now here's one at 6. A summary of the abundances. And what we were trying to do here is element by element simply show the bracket element to iron ratio. And again, put in your head that most of these are from neutral iron and neutral X element, except for the CNO, which is mainly molecular. Okay. Well, the first thing I say is, again, the optical and the infrared give roughly the same answers. The few exceptions we think we have explanations for, but mostly you get mostly solar abundances. They're not quite the same, and that's what we'd like to actually work on in the future here. But what we do here is now we have a complete expanse from wavelength 4,000 through 2.4 microns, and we're getting basically identical results, such that building toward highly reddened clusters, we feel confident that we don't need the optical. The reason why this MMU 152 was chosen, it is really unusual in its sort of elements that can be changed by stellar evolution. Again, what we first noticed was the very low carbon isotope ratio. What is then apparent is, wait a minute, of all the stars in NGC 6940, it has the lowest carbon. It has the highest nitrogen, although there's someone competing for that honor. No change in oxygen. Sodium, it's got the highest sodium. It's got the highest aluminum. Those are signatures of high temperature hydrogen burning. And again, that is not supposed to be happening in ordinary relatively high mass and very much high metallicity stars. So in the cluster, there is one star, one red giant, that is absolutely different than the others. And the interesting thing is that Elena Pancino published in 2018 a paper in which she claimed that rapidly rotating main sequence stars in open clusters, just the rapid rotators, tended to have high sodium. High sodium. And she thought enough of that to publish a paper on that. I suspect that what we're seeing here is a red giant, aged kind of star that Elena was talking about. Probably it lost its rotation as it ascended the red giant branch. I wouldn't be surprised if we have found one of her stars there. And there must be others out there. We're not sure how they should be interpreted, but what we are sure is they do exist. Only a few remarks on the interpretation. It's that we enlisted the work of the Victoria Stellar Evolution Group, that is Vandenberg and Denisenkoff. And I won't bother to explain these because life is getting short here, but really what it says is they were able to interpret correctly the age, the reddening, the evolutionary status of all our giants. And it's very nice work, and I really recommend that you go take a look at that. I learned a lot about stellar evolution by them explaining all this. Light element predictions, they can predict the CNO, compare them with our abundances. It's very nice work that they did. Two slides on NGC 752. We've just submitted that paper for publication, the Igrens work on it. And here we just show a comparison, the difference between the X to FE ratios of 752 and 6940. And I think you could say, well, they mostly get about the same. There seems to be an offset of about 0.05 dex. That's really my limit of being able to do this work. I know that someone really dedicated could probably squeeze that difference down or explain it better than I can. But for now, I just leave you with a couple of exceptions, most of which we understand. We get the same pattern, only a slight difference in bracket X to FE in the two clusters. I think enough to say almost identical. That's one thing I wanted to point out. And the other thing, back to the temperature calibration. Obviously, I think that's important. The lines in neutral species, which are what we see out in the infrared, really are temperature sensitive. And here are the two clusters. This is the same thing you saw before, temperature spectroscopic versus the line depth ratio. Yeah, they're about the same, okay? What's interesting here is, watch out, you Gaia worshippers. The Gaia astrometry is, of course, first rate. They really work on it. They have auxiliary information for not all of the stars, but for many of them. And they even estimate temperatures. And when you can say, oh, the Gaia and our temperatures and LDR temperatures for NGC 752 look exactly right. What is going on with the comparison for NGC 6940? What I suspect is going on is that a difficult time of accounting for reddening. I can't prove that to you, but clearly this is a mess. It's not even a correlation here. It's just sort of garbage. So be careful. It's not that, I mean, Gaia did good work, but just be careful on some of their auxiliary thing. So I'm almost done. It's been some labor doing these first two clusters. We have one more laborious cluster to do, M67. And we're going to work with Apogee people, because Apogee has already published a paper on M67. We're going to be working with them because Igrens gets broader wavelength coverage, higher spectral resolution. And so we're going to try to calibrate the Apogee results for metal-rich giants here. And I just list the other things. There's such a lack of good atomic lab data. So Paul Barkley, who's done a lot of good work on damping for atomic species, he's going to be working with us on the infrared. We already have data for Tripler 5 and Berkeley 17. We're plunging into more reddened clusters. And there's even this bulge, so-called glimpse cluster, that we now have data for. And we're trying to, we can't figure out whether it's a globular cluster or an open cluster. But we're working with the NOAO staffers, Hui and Ricardo. We are going also away from the Galactic Center. Bruce and Barbara Torog published a very nice paper on the relatively metal poor, that's minus 0.3, outer halo cluster, NGC 2506. We now have giants there. And then we are going to be hacking away at Gemini South proposals. We can reach the LMC, red giants, at resolution 40,000 in the Magellan Cloud. And we can also penetrate the bulge a lot. And all those data are in-house. What we need are slaves to do all the analysis. And the slaves usually are people like me and Melike. Okay, summarize the very red results. That is, we not only have a good new high-resolution spectrogram, we have now been able to convincingly show that it works very well for cool stars that are metal-rich and metal-poor. And we believe that we have set the stage for going to highly reddened clusters where people have never been able to use high-resolution spectroscopy before.
The STIS spectrograph is supposed to work on
Yes.
to observe beryllium lines too. So when it to be commissioned and
Sorry, for which thing?
the STIS spectrograph to be
At
at SOA.
Oh.
So yes, so
I don't know. When
yes,
is it? When is it ready?
It's in commissioning, so
Yeah.
it's probably would start it will be offered
Tomorrow.
to community. Not tomorrow, but next semester, I think.
There is an English word that I actually had to look up when I was trying to use it in an email, and I realized I wasn't sure of its definition. I wanted to say something to somebody saying, I will work on this anon, A-N-O-N. And I looked it up, and the online dictionary said anon means immediately, soon, or sometime in the future. And I've loved that. So yeah, I understand these things take time. The Egglands was a long time getting ready. I think it took 10 years to develop the gratings and actually getting a working thing. So, but yes, if it will go, if the SOAR thing, it doesn't need to be monstrous resolution, but if it can go down to near 3,000 angstroms, that is really good.
Please, thank you very much for this nice talk.
Just for curiosity, you show the spectra, the lines to derive the oxygen abundance. You said that it's possible to use in the optical the forbidden lines, and also using the Igrens, the OH lines, yes?
Yeah, maybe I didn't do it. Okay, let me summarize very briefly. Again, the thing stellar spectroscopists do not tell anybody else, no cosmologists ever hear about this, no planetary people ever hear about this, is that there are many elements for which the number of transitions you're using to get the abundance is very small. And none is worse than this than for oxygen. You see all these plots of oxygen as a function of metallicity. So almost always they are derived from red giant spectra, fine, of one line. There's a forbidden oxygen 6,300 angstrom line that is used all the time. And it's supposed to be perfect. Because most of the oxygen is down in the ground state, in the neutral, and the forbidden line should give you a perfect oxygen abundance. But in 2002, I think it was Allende Prieto, Lambert, and Asplund published a paper saying, we need to revise the solar oxygen abundance down by 0.2 dex. And come on, it's the sun, folks. And 0.2 dex, why? Because they were the first ones who really noticed that it's blended with a nickel transition. And as you go down in temperature and go up the red giant branch, fine, that nickel transition gets weaker and weaker, to be replaced by CN all over the place. So that line is very, very difficult to do properly. Out in the infrared, you have OH. And the problems with OH are, remember, it's a very much minority species. But there are 20, 30, 40 lines. So I think that using OH to get oxygen in red giants is no worse than using that forbidden oxygen line.
Okay, my curiosity is about a technical problem. Because, for example, if you have the forbidden lines in the optical, is it possible to consider the contamination from air glows or something like that? Because all the time you have also the contribution from the atmosphere. So
that's even worse, isn't it?
Yeah, and in my other question is that we also have another line in 5577 that belongs to the same triplet of the oxygen one. So is it possible to use that line too?
Okay. We're talking the details now, folks. Please bear with us. Look, there are three lines. There's the 6300, which everyone uses. There's 6363, which has a lot of CN, and it's 5 times weaker. And then there's, as you say, 5577. Problem with that one is that it appears to have NLTE problems, and it is messed up again with telluric line emission. You know, when you're working with the 6300 or 6363 lines, the problem is our night sky glows in those lines.
Yes.
And so if the radial velocity is low, throw it away. You'll never get it properly done.
Yeah.
But yes, all these lines have their own unique problems. You say, well, what about the triplet of neutral oxygen? Out at 7770 to 7775. Trouble is, the excitation and potential of those is like 9 volts. It's non-LTE problems are hideous for those lines. So you end up wondering, should you believe anybody's oxygen? Now, it's such an important element that we keep trying the best analysis we can. I feel much more comfortable if I have both the forbidden line and the OH. They tend to give roughly the same answers. They're not perfect, but at least I'm not totally crazy when I get the abundance from the forbidden line.
And considering the OH, there is no problem with the telluric correction? You need to take care.
Of course, in the infrared, a point I glossed over a lot is that yes, there are lots of telluric features. However, they are generally pretty well taken care of. Moreover, since you have so many of the OH lines, you can simply ignore the ones that you think are contaminated. And so it works out pretty well.
You mentioned about the abundance of ion group elements using HST data. So, can you use now? Can you still use optical data?
Yes.
From metal poor star?
Yes, yes.
Since
In
you
other
have,
words,
since you have
Right.
neutral and ionized species.
yeah, I mean, there's nothing wrong with the optical data when you can find the lines.
Okay.
For instance, you will not find any ionized cobalt lines, except way down in the ultraviolet. You will find very few ionized vanadium, maybe below 4,000. The problem is just getting lines, and you struggle to actually detect any. But no, you should get, when those rare elements in which we were able to detect lines, neutral and ionized, from the optical all the way down to the ultraviolet, they give the same answers.